1.4 quadratic equations. This time we're going to look at completing the square. Okay, completing the square is another method that we can use to solve a quadratic equation, and it works extremely well, especially in cases where you don't just have that quick, easy factoring that can be done using the zero product rule. Now, you may notice as we go through this that it's another valid method to solve things where you're using the square root property. And it'll come out in a similar way. So the idea of completing the square, the first thing we want to do when completing the square is we want to get the leading coefficient to 1. So basically, if we have ax squared plus bx plus c is equal to 0. So yes, we always start out with equal to 0, right? We look at this leading coefficient. If a is equal to 1, then we can go forward. If a is not equal to 1, then we divide everything by a. So a key part of completing the square is the leading coefficient must be equal to 1. Luckily, dividing everything by a is really easy, and 0 divided by a is 0. So we divide it out. This is going to end up being x squared. That'll be b divided by a, x, plus c divided by a. So it's going to move us into x squared plus some value times x plus some constant term is equal to 0. So dividing is nice. So that's the first thing we're going to do. So always make sure your leading coefficient is 1. If it's not, divide it out so that it becomes 1. The second thing we're going to do is we're going to move the constant term over to the other side of the equation. Now I know this kind of throws in the face of what I said previously of you always want that 0 on the other side. Well, with completing the square, we're going to move this constant term over. And we'll see in a little bit why that is. But we're going to get that out of the way because we want to complete the square. So once I've got that over there, I'm going to have x squared plus, and I'm going to just use another variable d, dx equal to some value over here. I'm going to call it e, just for the sake of something to put there, right? Because if a was equal to 1, then that would be negative c. If a was equal to some other value, it would be negative c over a. So it's just going to be some constant. So when we're in this form, x squared plus dx is equal to some constant on the other side. So why do we do this? Well, we do this because there are a couple special products that are going to help us out in being able to factor this. And those special products are a plus b squared is equal to a squared plus 2ab plus b squared, and a minus b squared is equal to a squared minus 2ab plus b squared. Basically, if I can get myself into the position where I have a squared plus 2ab plus something, if I can find out what this something is, that b squared term is, I can take this quadratic and turn it into this product. Same thing if I have that difference there. I can take the quadratic, turn it into the product. So our goal here is actually to put this x squared plus dx into this form right here. Make it match those first two and determine what value this needs to be to complete this perfect square. Right? This is a plus b squared. That's a perfect square. You take a value and square it, you get that. So that's going to be our goal. Well, how do we do that? We take this middle term. Notice that it's 2ab, right? We take this middle term and we divide it in half. So we're going to divide that by 2. And then we're going to square it to get this other piece. Because this is actually going to be the constant term that we're going to create. Once we've done that, we can then rewrite this in terms of a plus b squared. So we can write it as the square of a binomial. Once we have that, we can start manipulating and get to the final result. Now, I know written like this, that's a lot of letters being bounced around and not much to it. So let's actually take a look at this and see what happens, because this is definitely an example where seeing it actually done makes a heck of a lot more sense than just hearing it and some variables being thrown up. So let's grab some here. I'm going to grab an example. So x squared plus 10x minus 20 is equal to 0. So we start out with this. I'm just going to make this 10 a little more apparent. 10x minus 20 is equal to 0. So the first thing we do is we look to see if this leading coefficient is 1. In this case it is 1x squared, so that's good. So we don't need to divide it out. The second thing we're going to do is we're going to add 20 to both sides. We're going to move the constant term over to the other side, leaving us with x squared plus 10x is equal to 20. Now, I'm going to take this 10 and I'm going to divide it by 2. 10 divided by 2 is equal to 5. And I'm going to square that. 5 squared is equal to 25. So I'm going to say plus 25. Well, if I add 25 to this side, I need to add 25 to that side, right? I can't just add a 25 here and ignore it on the other side. But the addition property says if I have an equation and I add the same value to both sides, then I have an equivalent equation. Now that I have that, I have x squared plus 10x plus 25. Remember I said with the special products that we want to look for perfect squares. Look, we have x squared, 25, which is 5 squared. So we have there. So that becomes x plus 5 squared. Just to make sure I'm not lying to you, and I'm going to erase this once I'm done here. X times x is x squared. X times 5 is 5x. 5 times x is 5x. 5 times 5 is 25. 5x plus 5x is 10x, and we get x squared plus 10x plus 25. Boom. So this is the purpose. This is what we're doing. We are turning this into a perfect square. And we have this number off to the other side. But that's okay. Because now we're not dealing with just plain factoring. We're saying, okay, x plus 5 squared, so this here is the same as that, is equal to 20 plus 25 is 45. Right? So now, using the square root property, I can take the square root of both sides, giving me x plus 5 is equal to plus or minus the square root of 45. Now this should start to look familiar from what we did with the square root property. So x plus 5 is equal to plus or minus the square root of 45. So if I subtract 5 from both sides, I get x is equal to negative 5 plus or minus the square root of 45. And we have now solved this using completing the square. But Mr. Davis, could we have done this the easier way? And actually, this can go a step further. 45 is 9 times 5. So I could clean this up just a little bit and say x is equal to negative 5 plus or minus 3 square root of 5. Right? 9 times 5 is 45, so square root of 9 is 3, so I can pull that out. So this would be the most complete way to do it. If I can pull something out of here, do so. But can I do this another way? Well, what are two numbers that multiply to negative 20 and add to 10? Well, if they multiply to negative 20, they both have to have opposite signs. And if they add to positive 10, then the larger one has to have a positive sign. When we get into this, there's not much more I can do between, there's 20 and 1, so positive 20 and 1, which isn't going to work. And there's 10 and 2, which already puts me the other side, so it's obviously not going to work there. But this is our process, so completing the square. Let's try another one. We're going to take a step further, and we're going to have one that does not have a leading coefficient 1. What if we have 4x squared plus 6, oops, got carried away, plus 6x plus 5 is equal to 0. Okay, so 4x squared plus 6x plus 5 is equal to 0. Well, what's our first step? Our first step is we want a leading coefficient of 1. So what am I going to do? I'm going to divide through by 4. 4 divided by 4. So I can even do that for you just to, so you have the visual of it, right? 4 divided by 4 is 1, leaving me with x squared. 6 divided by 4 is 6/4 or 3/2, plus 3/2 x, plus 5/4. Okay, so there's my start, equal to 0. Because if I divide 0 by 4, I obviously get 0. 0 divided by any number is going to be 0. So now that I've got that, I've got a leading coefficient 1, well I need to move the constant term over. If it's plus 5/4, I need to subtract 5/4 from both sides. So x squared plus 3/2 is equal to negative 5/4. So we got that over to the side. Now we want to complete this square, which means we're going to, oops, don't lose the x there. Which means we want to divide this in half. 3/2 divided by 2 is 3/4. So 3/4. So that's half that. We want to square it to find this last term. So 3/4 squared is equal to 9/16. So we're going to add 9/16, which means we're going to add 9/16. So we've got that there. So now we can treat this as a perfect square, which you have x squared and you have 3/4 squared. So x plus 3/4, the quantity squared, is equal to, and over here we have negative 5/4 plus 9/16. Well, to make that work, let's find a common denominator, which would be 16. So I'm going to multiply top and bottom this by 4. So I get minus 20/16 plus 9/16, which gives us negative 11/16. I just want to make that look a little more like a 6 rather than just a blob. So that's negative 11/16. So minus 11/16. Now, we can use the square root property. So take the square root of both sides. X plus 3/4 is equal to plus or minus the square root of negative 11/16. Now, there's a couple things we can do in this. First of all, I notice that I've got a negative here inside my radical, which means I can pull that out as an imaginary number. I also notice that I've got 16 in the denominator, which is a perfect square, so I can actually rationalize the denominator just by taking the square root of that. So I'm just going to take that as my next step. X plus 3/4 is equal to plus or minus I, and then radical 11 over 4, and then I want to subtract 3/4 from both sides, so x is equal to negative 3/4 plus or minus I radical 11 over 4. Now, since this is a radical and a fraction at the same time, it's completely appropriate to put the I afterwards. And some people may like to put this whole thing over 4, but that doesn't leave it in terms of a complex number. That leaves it as a quotient in there. So I would say the most correct thing to do at this point would say that x is equal to negative 3/4 plus or minus the square root of 11 over 4i. That would be my considered most correct form to leave this in. So you can see that we completed the square. Now going through the process again, what did we do? First we divided by the leading coefficient to make it 1. That put us to here. Then we moved the constant term over to the other side, which happened here. Then we took half of this coefficient and squared it to get the new constant term. So we take half of this, 3/2 over 2, right? Or 3/2 divided by 2 over 1, which is 3/2 times 1 over 2, which gives us 3/4. That's what we did to get this value. We just took half of that coefficient. Then to get this one, we just squared that value. And that put us into the point of having our perfect square. So now we could say x plus 3/4, this value that we got here, squared, which allowed us to use the square root property, take the square root of both sides, which means we're going to put plus or minus in front of the radical. Since we have a negative here, we can pull that out as an imaginary number. Generally, you like to rationalize the denominator. In this case, it happened to be a perfect square, so that was nice. We could pull it out. And then the final case here, we moved over that 3/4, got it onto the other side, and then cleaned it up. So we're in the form of a plus or minus bi. So in form of a complex number. So that's a method that we can use for solving quadratic equations, completing the square. It works very well as long as you remember these steps. Make the leading coefficient 1, move the constant over, divide by 2 and square it. Now you've got a perfect square. Finish solving. Okay? Quadratic equations, completing the square.